Hello class, today I'm going to make a video about hypothesis testing. Before I talk about hypothesis testing, however, I want to give a general overview for our process so far, right? So generally what happens in statistics is that we have a question that we want to answer. A lot of times this question is a big question, and in order to answer it, we need to collect some data and then analyze the data to make a decision. Okay. For instance, maybe I'm interested in the average weight of a penguin from South Africa. Maybe I want to know the average flight time that it takes to go from SFO to Las Vegas on Southwest Air. Maybe I want to know the average weight of a Hyundai Sonata. Right? Because every time they make a car, it'll be slightly different than the last. So in order to answer these questions, I need to look at a population of things. Okay. And really what I'm interested in is some of the characteristics of this population, right? Either a mean value or something that helps me talk about the average value of the population is the standard deviation. Now, a lot of times our population is way too large for me to talk to or sample every element in the population. So randomly, I want to talk about a subset, okay, of this population. Something that's a little bit easier for me to get a handle of. And we call this thing a sample, right? For a sample to be a good sample, it needs to represent the population that it comes from, right? So in order to make sure that my sample represents my population, it needs to be random. Okay, the more random my sample, the better it represents the whole, right? So from our sample, we have the same characteristics that we have from the population. Your sample is going to have a mean, and it is also going to have a standard deviation. Okay. This is what we talked about leading up to our first test. What is the sample? What does it look like when you graph it? What are some of the characteristics? What kind of data are you getting? Are you getting data that's quantitative? Are you getting data that's qualitative? Where's the middle of the sample? All these kinds of things, right? What that does is it helps us to analyze the information, right? So we do some sort of an analysis and we can get some information about our sample. Once we get some of that information, we then want to use that information to talk about our population, right? And that step is called inference. Okay, we're going to use our small subset that ideally is representative of the whole, and we study this small subset, we analyze it to make some sort of a prediction or some answer some sort of a question about the entire thing by using what's called inference. And so right now we're talking about inference, right? The second half of the course we're doing a lot more of this analysis. We're looking at the common distributions that popped up. What are some of the more common things, shapes and distributions that my data looks like when I grab data and I analyze it, right? That was when we're doing the discrete distributions, the uniform, the normal, all of those things. So now we're taking this information and we're going to be inferring. We're going to make some sort of a prediction about the population from this subset that we grabbed. So an important way that we're going to do this is by using what's called the central limit theorem, right? So you guys have studied all this stuff already. This is just a review to help lay the groundwork for our discussion on hypothesis tests. The central limit theorem basically says that if you have a population and you grab from it a good sample, okay, the mean of this sample should be pretty close in value to the mean of the population, okay? And in fact, if you take a whole bunch of samples, okay, these samples can overlap, right? They can have a lot of the same elements in it. Okay, we take a whole bunch of these, and if we add up all of these average values that we get, and then we divide them by the number of times that we sample these things, we should get the same average of our population, and that should make sense. Okay, if my average drive time to school or work is about 10 minutes, okay, and I look and I record how long it takes me to get to work for a whole month, all of them should be around 10 minutes. Okay, that shouldn't be a stretch. That should make sense, right? So now when I take the average of these values, some will be more, right? Some will be less. There shouldn't be too many that are way off, right? But they should all be around 10. So if I average all of the times I have over a month, it should be very close to 10 if 10 is the true average. So basically what the central limit theorem tells us is that if you take a bunch of samples and you average those things, their average values should come out to be the same as the average of your population. Okay? So why is that important, right? That's really the question. How are we going to use this? Well, this is important because if I take a single sample, or if I take a single element from my population, right? And this is the mean of my population. A single element can be very far from the mean. It can be close, right? But it wouldn't be unusual to have a single element very far from the mean. However, if we use the CLT and we look at the distribution of all of the means I can have, okay, what that means is that if I grab a sample and I take an average value of that sample, the average value of that sample should be very close to my true mean. It should not be very far because I gathered a lot of data values and I averaged them together. Their average should be close to the true average. Okay? And so that's the basis of a hypothesis test. If I gather an average from a sample and that average value is very far from what I'm suspecting the true average to be, the true mean to be, one of two things are wrong. Either my sample is way, way, way incorrect, or my assumption of what the population average is wrong. One of these is wrong. My sample is way off because of something being broken or incorrect or me making a mistake, or my assumption about the population is the thing that's wrong. One of those things have to be incorrect. And that is what a hypothesis test is. You are testing whether or not this is unlikely to be true, or is this more unlikely to be true. Okay? And that's what we're going to be talking about. So all of our formulations are going to be based around this, right? How close is my mean? If it's too far away, if my mean is too far from my population mean, how far is too far away, right? If I expect my average drive time to work to be 10 minutes, okay, and then I gather a random sample of data, right? I record myself going to work every day for a month, and that average value for my 30 days of going to work is 25 minutes. That's pretty far from my expected value that I would think of, right? If I'm expecting my average to be 10 minutes, but I add up 30 days worth and I take the average and it's 25, that's not okay, right? What if my average was 20 minutes? Well, that's closer to 10 minutes, right? But is it still too far? What if it was 15 minutes? Okay, well that's closer to 10, but is that still too far? For an average value, right? Not one single value, an average of 30 values, 30 days worth average. Okay, what if my average is 10 minutes and 30 seconds? Is that too far? Right? How far is too far? And that's what we talk about when we do our hypothesis test. we have what we call an alpha value, which lets me know how far is too far. Right? So we'll do a hypothesis test next. I just wanted to give you guys a brief preview and an overview of what we've done so far and how that's going to lead into hypothesis testing. Alright, so let's go ahead and do an example, and we'll work through this pretty slowly, and I'll explain everything as we go. Right? So according to the American Diabetes Association, 23.1% of Americans aged 60 years or older had diabetes in 2007. A recent random sample of 200 Americans aged 60 years or older showed that 52 of them have diabetes. Using a 5% significance level, perform a test of hypothesis to determine if the current percentage of Americans that are 60 years or older who have diabetes is higher than it was in 2007. Okay, so what I like to do, whenever I have any kind of a word problem, which we have a lot of in this class, I like to pull out the useful information and I label it. That way I can use it as I progress through the problem. Right? So what do we have? So we have 23.1% of Americans aged 60 years or older had diabetes in 2007. To me, that looks like it is a proportion because it's a percentage, and they're talking about a population where the population is Americans that are 60 years old or older in 2007. It's a very specific population, but that's the population that they're talking about. So my mu here is 23.1%. Okay, that is a proportion that they've given me. Right. Next, we see that a random sample of 200 Americans. Well, it's very clear here that N is 200. That's how many people have been sampled. Showed that 52 of them have diabetes, right? So that's the number correct out of the 200. 52, right? So my mu in this case is P. My P hat is always X over N, or 52 out of 200, right? So that's the information I have so far, and I can write this as an exact value. Give me a second. You calculate that, so that's 0.26 or 26%. Okay, so that's my P hat. What else do we have? We're using a 5% significance level, so alpha is 0.05, right? 5%. Perform a hypothesis test to determine if the current percentage of Americans age 60 or older who have diabetes is higher than that in 2007. So I have my useful information. If I clean this up a little bit, right, my assumed average value is 0.231. My P hat is 0.26. I have my N value, which will come in handy later, and my alpha, 0.05, right? So this is the useful information. I'll try my best to keep this here, although I'm limited on space. So I'll try to not erase this as I erase other things, okay? So the first thing that we always want to do is we want to state our hypothesis, okay? Generally, we would state this in words and in symbols. I don't really care if you do it in words or not, but I 100% want you to do it using symbols, right? So our hypothesis, okay? So my null hypothesis, the thing that I assume to be true, is I think that the proportion is equal to 0.231, okay? It's what we're assuming to be true. I assume that this is true because there's a study that did it beforehand, and this is the value that they got. It was a professional study, so I'm assuming that they got this thing correct, okay? I have my alternative hypothesis. We can call this H1 or HA. It doesn't really matter, right? But it's my alternative hypothesis. And it has nothing, I mean, it does have to do with this 26%, but I don't write it in here, okay? I think that the percentage is higher than what they're saying. I don't think that the true percentage is 26%. I think it's higher than what they're claiming to be, right? I ran a study, or there's a second study that happened, and they got a different result, right? So my assumption is that it is actually larger than 0.231. So that's how we form the null and the alternative. It has to do with our population proportion or population mean. Okay, so we don't change this value. Our null hypothesis should always have an equal sign. Okay, you can say less than or equal to, greater than or equal to. It doesn't matter. You can always go with just equal to, and you'll always be correct in that statement. Okay, our alternative is that we are strictly larger than this value or strictly less than this value. Okay, and that is the relation between the two. Right? Now, the next thing that we're going to talk about, the test type. Okay, this is what kind of test? Well, I'm doing a test about proportions, and this larger than in my alternative is telling me that I will be doing a test for things that are larger than this value. Or on the right hand side, if I were to look at a graph, right? Things that are on this side of my average value or my mean value or what have you, right? So this will be a test for proportions, and it will be a right-tailed test, right? So this would be a right-tailed test of proportions. Okay, so I have my hypothesis statement. I have my test type, right? So the next thing that we want to do, is verify our conditions for the central limit theorem. Okay, verify conditions for the CLT, right? Now this is actually a very important step. It's left out a lot of times. Our whole test is dependent on the central limit theorem. I gathered a sample and I found a mean, right? Or a proportion from a sample. And I'm using the sample value to compare it to the population of sample values of that same size, right? So I'm using the central limit theorem here to compare an x bar or a p hat against a mu. That's central limit theorem. I can't use the central limit theorem if I don't have the conditions that meet to use the central limit theorem, right? I can't get in my car and drive away if I don't have the conditions to get in my car and drive away. I have to have a car. I have to have my car keys. I have to have a driver's license. I have to have gas in the car. There's certain things that have to happen in order to be able to get in the car and drive away. In order to use the CLT, I need to make sure I have the conditions for that to even work, right? So that's what we're going to do right now. Okay, so I cleared the board a little bit. We're going to verify the conditions for the central limit theorem, right? There's three things we got to verify. They're a little bit different if we're using the t distribution, if we're doing a test for means where we know the standard deviation, or if we're doing a test for proportions. It's a little bit different, but it should be stated in your book, in the OpenStax book. So first thing we need is randomness. Okay, so remember at the beginning, I said a good sample has to be random, because if it's not random, then it does not represent my population, right? So there's two ways to do this. Either it will be stated that it's random, or our test will be conducted by a professional institute, that conducts research for a living, right? So here, our sample was of 200 Americans. Okay, it was not coming from the American Diabetes Association. That's where we got our population information, right? Here we have a recent random sample. It doesn't say where it's collected from, but it is stated that it's random. So we can say that, right? So we can say that it's been stated a random sample. Okay. The next thing that we need to have is independence, right? We're using rules of probability, laws of probability, and laws of probability are really based, the ones that we use are based on independence. So I need this to be independent. The sample needs to be independent. Okay. So each element in my sample cannot be reliant on the answers of the other elements in my sample, right? The way that we do this is we have a small sample from a large population. Okay. If you ask me a question about how much food I ate yesterday, and you ask someone in New York about how much food they ate yesterday, both of those things are very random. We're randomly selected, and we're very, very far apart. And we're a small sample, 2 people out of the entire population of the world, right? So a small sample from a large population that's been randomly collected will ensure that each element is independent of the last. Okay, so we just say a small sample from a large population is fine. The next thing that we need is normality. Okay. Okay, the central limit theorem is based on our distributions of means or proportions being normal, right? So if we don't have a normal distribution of our means or proportions, we can't do anything that we need to do here, right? All the graphs that we have, as you've seen, are shaped like this, okay? Normal distributions. So for normality from proportions, we have 2 things. My expected number of successes and my expected number of failures from my sample should be should be more than 5. Okay, I should have more than 5 successes and more than 5 failures. Okay, if I'm expected to have all successes or all failures, then everything is skewed too much and I can't have this, right? So the way we do this is we look at the expected value. NP larger than 5, NQ larger than 5. Okay, here P is 231, right? Because I know, or I'm assuming I know, what my population proportion actually is. I'm not using my P hat because I'm using this proportion for my sample that I gathered. Okay, same with my failure rate. So here I have 200 times an expected proportion of people, 231, saying yes. And it's very obvious here without even doing the math that this is in fact larger than 5, right? And the number of people I would expect to not have diabetes is 200 times, and then whatever the complement of this is, right? So 0.769, right? 76% of this, of 200, is obviously less than 5. So we can say, therefore, our distributions of proportions assumed approximately normal. Okay, so that's how we know that we have the conditions. Expected number of successes more than 5, expected number of failures more than 5. If we were using, if we're looking at means, I would need to have that my sample size is larger than 30, right? But we're doing proportions, so obviously my sample size is going to be more than 30 here. Okay, so the next thing that we want to look at, or that we want to state, is my level of significance. Okay, level of significance. Okay, So this is the value. This is basically my value that's too large, right? So remember before I said how large is too large? This is that value. And it's actually given it to me here, right? 5% level of significance. So we just say that, right? So we would say we're testing at the alpha equals 0.05 level of significance. Okay, so a question that comes up a lot is, why do I have to write all these, and why do I always have to write them as a sentence? A hypothesis test is a report. Okay, so you're basically writing a report on why you think the answer to this question is whatever it is that you think it is, right? How did you come up with this conclusion, and why is this conclusion what it is, right? So everything that we write is going to be read by somebody eventually, right? That's our thought process in this course. So when we write these out, we want to write full sentences, and we want to write clearly and thoroughly. Okay, the next thing we're going to look at is the test statistic. Test statistic. Okay, this is basically, not basically, it is the data value. Okay, it's the z-score for our data value, right? Our data value here is that p-hat value. That's the value we're testing across this. So we want to take this and we want to look and say, how far is it from my expected value? So we're going to turn it into a z-score, right? So we call this z of p-hat. We know the formula for this. So it is my sample statistic minus my population parameter over the standard deviation for my population. Okay, and when we don't have this, that's when we're doing a t-test, right? So here we can simplify this even further to pq over n square root, right? So we have 0.26 minus 0.231 over, so for my test statistic, my parameter, 0.231 times the complement of that, which is 0.769, okay, over my n, 200, and we can get this value. Right, so let me calculate that real quick. Okay, and the value I got for my z-score is 0.97306. So we round that to 1. Okay, so what I'm going to do here is I'm going to start to extend my little collection of values here. And I'll just write this because, as you can see, I've been erasing stuff as I go. So the important values I'll keep here, right? So my z-score for p-hat, my test statistic, right? This is what I'm going to be using to compare in my graph, in my population, is 0.9731. Okay, so that's what we have so far, and I'll be adding to this again also in a little bit. But that's what we have. Okay, so now I have enough stuff to do my next thing, my graph. Okay, ideally I would find my p-value next, but we'll draw a graph and then we'll add our p-value into the graph, right? So the next thing we want is a graph. So in all of our inference that we do, confidence levels, all the different hypothesis tests that we'll do, the graph is very important. Okay. When I'm looking at your exams, I really should be able to look at your graph, see all of the important information, maybe not n, but definitely your alpha, your p-hat, and your z-score, and your p-value also, which we'll talk about. All of those things should be in your graph. I should be able to look at your graph and say, okay, you got this answer right? I should be able to just kind of breeze through it. I mean, I'll read your questions, of course, but your graph should display to me all of the information and all of your results. Okay, so after your graph is done, you're really just kind of writing things out and explaining them, right? But your graph is like the meat and the potatoes of the test. It's says everything that's happening in the test. Okay, so let's go ahead and draw our graph. Okay, so if we draw a graph here, and I'll draw as best as I can. I'm not the most accurate with this pen and tablet that I have. Okay, we'll have a normal distribution. And I'll rewrite this again once we do our p-value, and I'll again include all these values that we have here, and then show where the p-value fits into that. Okay, so I should have my parameters from my population, right? Because that's what this is showing me. So I'm going to have here my population mean proportion, right? 0.231. I should have the standard deviation for my population, okay, which we'll talk. Okay, so I calculated real quick. All right, so this was the PQ over N root portion from my Z of P hat. So if we calculate this, it is 0.0298 if we're doing 4 digits. Okay, 4 digits is pretty nice for us. All right, so this is my value here. It was the denominator that I had for my z-score, right? So let's clean this up just a little bit, just so I can. Okay, so this is my distribution for what I have going on here, right? So this is my population mean, and this is the or proportion, I'm sorry, and this is the standard deviation for my proportions, right, using CLT. Now, if we look at this here, okay, I have an alpha value. The alpha value tells me how much area is in the tail of my test, okay, and we call this thing the rejection region. Rejection region. Okay, anything that lands in this area is too far away from my mean. Okay, now let's think about this. This is a z-score. Okay, my p hat value is 0.261. So my p hat value is somewhere over here. Okay, 0.26. The problem is I don't know what this value is. Okay, what is that value? What is this critical value? Now I can figure this out by doing inverse norm using these values, which is okay, right? Maybe we'll do that. But I can also do this by doing inverse norm and using z-scores, especially since I have a z-score. I prefer to use these using z-scores instead of the data values, but we can do either one. So real quick, right, I drew this p hat value over here, but it could very easily be too far. I don't know where the cutoff for this rejection region is, right? So let's figure this out, okay? Inverse norm, right? So I'm using the area over here. So remember, inverse norm only does the area up to a point, right? So I need to put in 0.95. What is my mean? 0.231, and then my standard deviation, which is 0.0298. And then when I calculate this value, it'll tell me what data value is my cutoff point. Okay, so let me do this real quick, and I'll write this on here. Okay, and so my cutoff value, where's my, there it goes. Okay, the cutoff value here is 0.28001. Okay, so this critical value here, okay, is 0.28. Any mean, any proportion, any p hat that I found that was over 0.28 would have landed in this area, my rejection region, and I would have failed my hypothesis test, right? I would have assumed it would have been very unlikely for me to get a sample value that far away from my mean. It would have been too far away, right? So what this is basically saying, I can basically make my conclusion from here. Okay, I don't even have my p-value, but I know that I'm not in rejection region. Okay, and I guess when I wrote this, right, I have to find out what that cutoff value is first, right? So since it's before the cutoff value, it's not too far away from my true proportion. So my null hypothesis, right, my assumption that I'm getting from the Diabetes Association, I would now assume is, I wouldn't say that it's correct, but I would say I don't have enough evidence to say that it's incorrect. Okay? If I've gathered some data and my data value was way far away from what they were telling me it is, okay, the likelihood of that happening would be very, very small, under 5%, right? So that would say that my data value, right, my test value, my p-hat that I found is way too far away from the true proportion, or what I'm assuming is the true proportion. So I would then assume that the true proportion is incorrect and it's actually larger than what it is supposed to be. Otherwise, why would I have a p-hat that is so large? That is not what's happening in this case. In this case, my p-hat is close enough to what I'm assuming is the true proportion for me to say that nothing is wrong. Okay? I do not have enough evidence to say that this 23.1% is incorrect and it should be higher. There's not enough evidence to say that that is what's happening. Okay? So it's kind of like when you're on trial for something, you're innocent until proven guilty. I don't have enough evidence to prove guilty. Guilty would be that this thing is incorrect. It's not far enough away. Okay, so that's what's happening here in a nutshell. We're going to write all that down, but that's what's happening. Okay, I had to find out the value that's too far away, and then I look at where my value is in relation to that. My value from my sample. Okay, this thing in relation to this sample. Right? Is it too far away? It's not. It's closer. It's not beyond this value. Okay. All right, so let's look at an alternative method of coming up with this conclusion, okay, or with this step of the graph. I made this graph the last time, right, just a second ago, using information from that was gathered, right? My population proportion, my sample proportion, my alpha value is still the same, right? This is still 5%, right? And so this shaded in area is still my rejection region. Okay, so anything that falls in there tells me to reject H naught, my null hypothesis. If it lands in there, I reject H naught, right? So another way of doing this, which I think is a little bit easier, is using the standard normal distribution, right? I have a mean of 0 and a standard deviation of 1. I have a z-score of 0.9731, and I need to know how far away is too far. So I would need to find the z-score of 0.05 in the tail of something. And a lot of times we have this value given to us already. If we don't remember what those values are by memory, we can always do inverse norm, and again the same thing, 9501, right, for those values. So it's one of the tails, not in both tails, right? Okay, and the z-score that gives us this value here, right, this z of 0.05 in the tail is 1.6449. Okay, so any z-score that is larger than this will land in my rejection region, and I already have the z-score. This is my test statistics. It's very obvious it's less than that, so that's going to be somewhere over here because it's more than 0, less than 1.6649, and so this would be z of p hat, which is 0.9731, right? So it does not land in the rejection region, which we already knew from the last graph. But a lot of times I like to just use 0, 1 because the default on your calculator, when you do inverse norm, it's already 0 and 1. We've already found the z-score. And a lot of times, these things are default. You already know what they are. It's highly likely that I just give them to you anyways. The z-score for the common alpha values, right? And then it's just very easy to put your graph together. It's much easier than using the data values. Okay. Now that we've made a graph, the next thing that we're going to do is we got to find the p-value. Okay. So the p-value is basically what is the probability that I am at this value or more extreme. Okay. So as you can see, this area in this case is more than my rejection region. And that's going to be true because I am outside of the rejection region, right? So my probability here will be larger than 0.05. If I were to have landed somewhere inside of my rejection region, then the area past that value would be less than 0.05. So the probability that I got this test value or more extreme is what my p-value is. Okay, so if my p-value is less than my alpha, I will reject because I'm in the rejection region. If my p-value is larger than my alpha, I will not reject because I am outside of the rejection region. That's why the probability is so large. Okay, so let's go ahead and find the p-value. All right, so p-value is the probability of getting our sample statistic that we got. In this case, it's the p-hat. If we're talking about means, it would be the x bar that I found, right? But I'm talking about proportions. So in this case, we're using p-hat, right? What's the probability that I found this p-hat or one even more extreme? So if we're doing a right tail test, what's the probability that I found this p-hat or one more extreme? If I was doing a left tail test, right? Meaning I think that I'm less than the true proportion, right? Let's say what's the probability that I got my p-hat or something even less than that. That's what the p-value is. The probability of my results or something even more extreme, more less or something more larger if I happen to be larger than my parameter, right, for my population. So in this case, again, we can do this in two different ways. We can use the data information, right? Our data values are our information from the population, or we can use the standard normal. I prefer to use the standard normal. I will show you how to do it both ways, okay? So my p-value is the probability, and again, this is what a probability statement is. It is the statement of your probability, right? What is the probability that I get a p-hat value that is larger than or equals to, it doesn't matter if I put the equal sign because it's continuous, 0.26, given that h naught is true. Okay, I'm assuming that this is true. That's why I have to compare it in my graph. Okay. All right, I'm assuming this is true. So what's the probability I get something more than my value if this is the true value? The probability of that happening is really, really small. That means I landed over here. I got a small probability of that happening. If the probability of that happening is large, well, then that's because my test sample was very close. So it makes sense that it was large. Right? So that's what's happening graphically. And that's what we will use here. Okay, so what was my values? So this was z of p hat equals, and I'll find that in a second. Okay, so for us to do this, okay, back to normal. So the probability of this is going to be normal CDF. Okay, from my sample value 0.26 to something very large with my mean, my proportion, my true proportion, because that's what I'm assuming is true. That's why I keep using it and everything. And then the standard deviation that I have, which is, oh man, this is 0.2831. Let me fix that in just a second. Okay, it was 0.0298. Right, so that was our standard deviation that we had for this distribution. So if we plug that into our calculator, we will get our p-value. Okay, and when you check this value, you should get 0.1652. Okay, which when you compare it to your alpha, 5%, it is higher than 5%, which we already showed from the graph. Okay, another way to do this, right, using the standard normal, still using normal, we will still get the same value. Okay, so I'll keep the value there, but our probability statement will be different, and the calculations we use will be different. We will use the probability. So now we're checking that we get a z-score that is larger than the z-score that I got, 0.9731, assuming that the null hypothesis is true. Okay, so when we use this, we'll use normal CDF again. Okay. Our starting value, 0.9731. Something very large, just has to be more than 10 standard deviations away, so I can do something like 1,000 in this case, right? Or 10 to the 99, doesn't matter, just something large. Mean of 0, standard deviation of 1. Okay, if you plug this into your calculator, you will get the exact same value that you got out last time. Okay, so let's add this to our useful informations, pieces that we're going to use here. So my p-value is 0.1652. Okay, so now what we're going to do is we'll state our conclusion, which happens to have a summary with it, and we will then write the possible errors, right? Because it's very possible that I'm wrong. It's very possible that the data that I got was skewed in some way. Maybe it was collected incorrectly for some reason. Who knows, right? Maybe I just got a really weird sample randomly, right? Because it's all random. There's all kinds of things that can happen, right? So we have to talk about possible errors that might have happened, okay? So what I want to do now is I want to come up with my conclusion, okay? Your conclusion should be stated in context of the problem, okay? So first thing we're going to do is we're going to compare our p-value to our alpha, right? Since our p-value, which equals 0.1652, is larger than my alpha, which is 0.05, we can conclude to fail to reject H0. I'm not in the rejection region, so I'm not going to reject my null hypothesis. We don't say that we conclude that H0 is true. Okay? We don't know if this is true. If we knew this was true, we wouldn't be asking this question, collecting data, and running this test. Right? We think something is up. We don't have enough information to say that this is not the correct thing. So all we can say is that our data fails for us to conclude that it is false. We just don't have enough information to say it is false. So we don't say that it's false, we just say we don't have enough information to reject it. Okay, so we can conclude to fail to reject, right? We failed to show that it's wrong, right? So we failed to reject the null hypothesis. What does this mean? right? What does it mean to fail to reject? So, there is not enough information to conclude. And what is it that we were trying to show, right? We were trying to show that the proportion of Americans that are above 60 years old or older who have diabetes is higher than it was in 2007. So that's what we'd write. Okay, so there's not enough information to conclude that the percentage of Americans above 60 who have diabetes is above 23.1%. Okay, that is what we failed to conclude. Right, so that's our conclusion. Right, so now we have to talk about our possible errors. We have type 1 errors and type 2 errors. Okay, so we'll talk about what the different errors were and what they mean as per our conclusion. Okay, so this happens to be a possible type 2 error. Okay, which is that we failed to conclude, to reject the null hypothesis when the null hypothesis was actually false. Okay, so basically we decided that we're not gonna say that this is wrong when in fact it actually is wrong. That's a type 2 error. Type 1 error is the other way. If we did decide to reject the null hypothesis, but the null hypothesis was actually correct, right? So if we said, no, our data is too far away from this for this to be true. This is wrong. It has to be larger, but it actually was this thing. That's a type 1 error. That's not what we did. We did the opposite of that, right? We said that our data collection, our test values, right, our data values were close enough to what we assumed to be true for us to say there's nothing weird going on, right? So we failed to say that there's something different going on when in fact this thing is not true, right? That's what a type 2 error is. So we wrote it in terms of statistics, but we want to explain this in the context because when we do this for a job or a professional paper, the average reader is going to have no idea what this thing means, right? So we want to write this in context, okay? So, what this means is that we concluded that there was not enough data to say and we want to come back up here and write in these terms, right, that the percentage of Americans over 60 with diabetes, right? So there was not enough data to say the percentage of Americans over 60 with diabetes is larger than 23.1% when it actually is. Okay, so that was our error. We concluded that there's not enough information to say that the average value is over 23%, but it actually is over 23.1%. And that's our full test. Right, so there's lots of elements. I've uploaded quite a few things that show you, that kind of outline those things in detail. But I noticed I didn't have a full example for you, so I try to explain everything from the beginning. I hope this was helpful. If you guys need more assistance with this, then I'll do a quick example with the mean, right, where we're doing something with means and not proportions. Proportions kind of throw people off sometimes. So do the t-distributions. So I wanted to do one that was a little bit more difficult. However, I'm going to be leaving tonight, so I'm not going to have access to my computer for a couple of days. I can still respond to emails. Happy holidays. I hope you guys have a good Thanksgiving. Let me know if you have any questions. I hope this was helpful. Thank you.